apsolutno plana prekrovizije, a ima gomilu nekih predmeta što možete da se ulogujete na studiju. Imaju odpreda ili odsluša. I to je što se studiju. Hvala vam puno.
Thank you very much. You're welcome. Okay, I'll go here and see if this works. Okay. Okay, this is working, right? Yeah, I didn't understand a whole lot of what Velko said, but hopefully it was interesting. So I'm happy to be here. It's my second time in Montenegro, and it's always good to be here. And this is my third lecture over here. Well, the first time in the University of Montenegro, so and the next one will be on genome analysis this afternoon. If you're interested in learning about genome analysis, you can come to it. But right now we're going to talk about hardware security. I was asked to talk about hardware security, and we do a lot of work in this area. But I'm going to give you a very specific aspect of hardware security that I think is going to be even more important into the future. Hopefully it'll be interesting. And how much time do we have? 45 minutes? Because this talk can take several days or 10 minutes. But if I do it in 10 minutes, I don't think anybody will understand a whole lot. But I'll try to do it 45 minutes or so, and then leave you.
45 minutes or until the bomb threat.
Oh. You know, I was giving a similar lecture at Samos, on Samos Island. There's a conference in Samos in July that I will go to this year also. And I was giving a keynote lecture in 2015. And I was taking a long time, and eventually the electricity went out on the island, and everybody was very happy. So something like that may happen here. You're suggesting it's possible, yes. By the way, that lecture is also online. You can see the electricity going out then. Yeah. Okay, so hopefully it will not happen, but I'll try to keep it short. I'll skip the very technically detailed parts because I think we have a wide audience over here. Well, I'll try to give you the key insight. So there are a lot of slides because this is a long talk that summarizes what has happened on something that we have been working on for a long time, as you will see. And hopefully the key insights will be there. Okay, so when I start talking about hardware security, especially in a freshman class, for example, I put up a picture that looks like this. Does anybody know where this is? Those of you who've been to the United States, this is very close to Seattle. First of all, it doesn't exist anymore because something happened to it. That's like a bit flip, a bit getting corrupt. Basically, this is what happened to it. It got destroyed because of some reliability problem. It's called the aerostatic platter. It's called the galloping Yordi. That's the nickname of this. Basically, this bridge used to do this for 6 months. It did that, and eventually it collapsed. And everybody knew that it was going to collapse, so there was no fatality over here. But I think this is an example of critical infrastructure that human beings have been building for thousands of years. And clearly we have reliability issues in this hardware, this heavy hardware infrastructure. And we want it to be reliable, safe, and secure. We don't want this sort of thing to happen. This happened in 1940. And now you can go to the same place. There are 2 bridges that are going. They constructed 2 new bridges. That's as a redundancy, right? If one of them collapses, the other one hopefully will not collapse. So this redundancy is one way of handling reliability, security, and safety issues. But this is a great example of a simple reliability problem causing safety problems and security problems. I'm going to show you some more examples, hopefully, when we get to the end of other bridges. But keep this in mind. This is another example that I use. These folks have constructed, I believe this is San Francisco, but I'm not sure. You can read the thing over there if you find it. Essentially, these guys are very happy right now constructing the city on the sitting on this rod. But if this rod has a reliability problem, they may not be very happy in that next second. So it's good to think about it this way. So I think of security in general as preventing unforeseen consequences. I like this definition because it's very broad. In a sense, this breadth is what encompasses security, in my opinion. Right? You should really be ready for some unforeseen consequence, like a bomb threat coming right now. How do you deal with it, right? That's a safety issue also, clearly. So these reliability, safety, and security issues are very tightly connected, even though they're different things. Let me give you another example. Does anybody know who this is? Yes? Anybody wants to venture? Mr. Lee. Okay, everybody knows. That's good. Nobody knows about the Tacoma Narrows Bridge. This was called Tacoma Narrows Bridge. I don't give you the exact name. It's close to Seattle, where I used to work in the past, Microsoft Research. But this is Mr. Bean. He's more famous, clearly, than that bridge. And this is his self-driving car. And this is a beautiful scene from one of his episodes. And this is a beautiful self-driving car. He's very happy. But if a problem happens, if a bit flip happens over here, he's not going to be very happy in the future. And of course, it's a joke, but this is what we're going towards. Basically, we're going to rely on this hardware that we're building, computers that we're building ever more into the future. And these are much, much more important and prevalent than bridges. Basically, one can say, I don't care about bridges as much. That's a tough thing to say when you have rivers around, of course. But if you have flying cars, maybe you really don't care about bridges, right? But now you have transformed the problem into a much bigger safety problem. Basically, this is much more critical infrastructure. Computing is much more critical infrastructure than what we've built for thousands of years, I would argue. And we should be much more careful with what we're doing with computers and how we're building. And this talk is about that essentially. If you don't take away anything from that talk, this is it, I believe. But let me talk about how this is connected to what I'm going to talk about. I'm going to talk about a very specific issue in memory chips. It's called Rowhammer. And this specific issue is that one can be you, me, or anyone here using the right programs. You can predictably cause bit flips in commodity DRAM chips. Basically change the value of data unintentionally from somebody else's perspective, because you're changing somebody else's data potentially. And at the time we first analyzed this issue, we found that more than 80% of the tested DRAM chips were vulnerable. Today it's 100% actually, as I will show you later. And this is actually a reliability problem. This is the first example of how a simple failure mechanism in hardware level can create a widespread system security vulnerability. So I'm going to tell you the story of it, hopefully. And this is one example of 2 years after we wrote the Rowhammer paper. This is a Wired magazine person writing a nice article. I like the title of this article. It says, "Forget software. Now hackers are exploiting physics." Basically, this shows the fundamentals of physics are actually very important in terms of maintaining secure hardware in the end. Okay, let me give you the story a little bit. So we were working on memory technology scaling. We do a lot of work on memory systems, but one of the aspects of memory systems is how does memory technology scale into the future? Can we actually make it better? Can we actually tolerate reliability issues? And we wrote a lot of articles, some of which I'm going to flash. I don't expect you to read them, etc. But this is one of the early articles that we were invited to write to this industry conference, International Memory Workshop, where we presented the work. And we argued that basically memory technology scaling is getting worse. Reliability is going to be a big problem. Safety and security will be affected by these reliability issues. So we should really have a bigger perspective. We should not leave it to the device manufacturers to solve this problem. We should have a systems architecture perspective, even a software perspective to solve these issues. So basically, let's take a look at a specific memory technology, which is in everyone's pockets right now. It's the DRAM technology. It's the main memory. And main memory consists of dynamic random access memory today. It's a specific technology that was invented in the 1960s. It's still strong. And if you look at this technology, data is stored in this capacitor. Basically, you have 1 bit stored in this capacitor, and then you have an access transistor to access the data, and then bitline and sensing structures. Basically, this is 1 DRAM cell. Now, for this to work reliably, this capacitor must be large enough for reliable sensing. And this access transistor and the bitline and the sense amplification structures should be large enough for low leakage and high retention time, and also good sensing at the same time. Now, if you reduce the size of the cell, both of these reduce. And today, actually, we're at about 10 nanometers or so in terms of size. And this capacitor doesn't look like this. This is a nice picture. What it looks like in a real chip is actually looks like this. I mean, it's not that big, of course, right? The size of that is actually almost 40, 50, 60x length compared to this transistor. And that's how people actually get these DRAM chips to be high capacity. In your pockets right now, probably have DRAM chip 64. I don't know how, quite large basically right now. So as you reduce the size of these, both of these properties become difficult to maintain. But so fundamentally, the technology becomes unreliable. And this is DRAM. We're going to talk specifically about DRAM, but this actually applies to any other technology. Any other technology, when you reduce the size of the cell that stores the data, it becomes unreliable. So as a result, the capacity, cost, and energy are hard to scale. Okay, so we actually wanted to understand the effects of this at the high level. So we did this study with Facebook. In around 2013-14, we published this paper in ESN 2015. Essentially, what we analyzed was in their production data centers, what kind of effect do we see in terms of the density of the chips? And this is a correlational study. This is production data centers, so workloads are running. And it's a lot of data centers, a lot of memory. They didn't allow us to write how much memory, how many data centers, because they were concerned that revealing this information would be bad for the stock price because it's a huge infrastructure actually. And if you see, the one takeaway of the study is that this is the chip density that's employed in the server, and this is server failure rate. This is the DRAM chip density. And denser chips, you can see that lead to or correlate with higher server failure rates. So this is real data from the field, essentially. It's interesting because I'll talk about it, but we don't have time to delve into detail. The reason is that denser chips have smaller cells and also cells that are much closer to each other. As a result, there's a lot more noise in the memory. So you get some bit flips once in a while for various reasons, which are discussed in the paper, but I'm not going to talk about those reasons. So essentially, there's evidence that in the large scale, you have problems. Okay, if you're interested in the paper, you can read it. It's written with Facebook, as you can see. Okay, so then later we also said, well, during the same time, actually even earlier, we were interested in understanding these problems at a small scale. So we built these FPGA-based infrastructures. This is our one of the first infrastructures. Essentially, you have an FPGA, you have a memory controller, you can have a soft memory controller, you can modify it. You can change the command sequence that goes to the DRAM chips and figure out what's going on. You can turn off refreshing, for example. DRAM requires refresh of cells. So right now, the memory in your cell phone is getting refreshed every 64 milliseconds. It's wasting energy, basically. I'm going to talk about that very briefly. That's the reason we wanted to build this infrastructure, to study what are the characteristics of these chips, how can we eliminate refresh, for example. And then we built newer infrastructures. Okay, this is one of the infrastructures where we did a lot of Rowhammer studies, and we actually open sourced it. This is in 2017. Actually, I don't have the slide for it, but we recently open sourced the newer version of it. That's even better. So if you want to actually do some studies, you can actually get a newer version if you're interested. Okay, so why did we build this infrastructure? We really wanted to understand how long data can be retained in a DRAM cell. So all of our cells are leaky in DRAM. It's like memory, human memory, right? Human memory is leaky if you don't use it, if you don't refresh it once in a while. DRAM cells are also leaky, and you need to refresh them very frequently. And this frequency is actually very bad for technology scaling. We showed in earlier papers that, for example, this one, that you need to refresh a lot more going into the future. So 50% of your entire memory energy and 50% of your entire memory throughput would be spent just refreshing the memory, keeping the data intact. You cannot access the DRAM during this time. So this is a big scaling problem, and that's the reason why we built this infrastructure. And one of the things we studied in this infrastructure is to understand the retention times of different DRAM cells. So today you refresh everything at the same frequency, 32 milliseconds actually, it's getting lower and lower. At the time it was 64 milliseconds. But we said, do you really need to refresh everything every 64 milliseconds? Some cells are actually much more reliable. So can we refresh them much less frequently? And that way we can actually improve performance and also reduce energy. And that's what we did essentially. Of course, this is easy, and this is because the retention time profile looks like this. Only a very small fraction of cells you need to refresh every 64 milliseconds. A vast majority of cells you can get away without refreshing 4x the rate, or 4x lower the rate. Unfortunately, this is not that easy. It looks very nice like this, but once you go and study the problem, this is not easy. It's location dependent, it's data value dependent on stored value, it's dependent on some random process. So there are quantum-like effects that happen that change the retention time unreliably very quickly. And you need to figure that out. So basically, this is the original paper where we said that you could actually do this. And then we wrote papers saying that, oh, we actually studied real DRAM chips. This is not easy to do. And then we wrote a lot of papers later on saying how to do it. I'm not going to bore you with all of that because these papers clearly are going on right now. And right now, actually, because of some of these things that we studied, like variable retention time, the quantum-like effect that I mentioned, manufacturers started adding error correcting codes inside the DRAM chip itself. We're going to talk about error correcting codes. So one way of actually getting rid of these random errors is adding error correcting codes. So this was a good idea to put error correcting codes in the DRAM chips. Okay, I will not bore you with this, but this is why we built this infrastructure. Actually, we built this infrastructure to study these retention time effects, which are fascinating. If you're interested, you can learn more about it. So going back to this infrastructure, while we were actually looking at this infrastructure, we also said that, oh, can we actually find other error mechanisms in DRAM, other failure mechanisms? And together with Intel, that's what we did essentially. We found out that you can predictably induce errors in most DRAM memory chips. And this is the Rowhammer phenomenon. I already mentioned all of this over here. Let's talk about what the phenomenon is. Essentially, it's a read disturbance phenomenon. In a sense, there's nothing new here. There's nothing new here in an extremely fundamental sense, meaning read disturbance is a well-known phenomenon in any memory technology. If cells are too close to each other, you break isolation. As a result, whenever you activate one room, some other row, cells on some other row actually get correct. Now, what's interesting here is this happens in real DRAM chips, and this gets exposed to software, meaning that immediately the user sees these bit groups. So if it was hidden from the user in some way, that would be nice, but it's not hidden, it gets immediately exposed. And it's getting much worse. So basically, the idea is memory consists of rows of cells. Each row has, let's say, kilobytes of cells. And if you want to read some bit over here, you apply high voltage to that row. This is called opening the row or activating the row. Now, if you want to read some other row, you deactivate this row, meaning apply low voltage, and you activate some other row. But it's perfectly valid to keep activating this row. Activate precharge, or open or close, open, close, open, close, high voltage, low voltage, high voltage, low voltage. Now, if you keep doing this repeatedly enough times before the DRAM cells get refreshed, it turns out some vulnerable cells and physically adjacent rows get correct. The data value that's stored as 1 becomes 0 usually, but it could be the other way around depending on the encoding that's done in DRAM. Now, clearly this should not happen, right? If I give you memory, and if I say you're just reading from memory and one row, nothing should change in memory, let alone rows that you're not accessing. So these rows can belong to someone else. These rows can actually have some security critical data. So essentially, we call this the hammered row, and we call these the victim rows. And we showed that more than 80% of the chips that were manufactured by 3 major manufacturers, and there are only 3 major manufacturers in DRAM today, Samsung, SK Hynix, and Micron, essentially. They occupy more than 96% of the DRAM market. They essentially all are vulnerable. So why am I telling you this? Because this is an industry-wide phenomenon. It's not a specific manufacturer phenomenon. Sometimes things happen, manufacturer does something bad, but this is really fundamental. It's a fundamental technology scaling phenomenon. So basically, the chips that we tested that were manufactured before 2010 were not vulnerable. At least we were not able to induce errors in them. But in 2010, we were easily able to induce errors, as you can see. And between the chips that were manufactured between 2012 and 2013, we can induce errors in all of the manufacturers' chips. So basically, as cells become smaller and smaller and get closer to each other, they become more vulnerable to this effect. So let me go into a little bit more detail. And basically, the key thing is DRAM cells are too close to each other, and they're also small. They're not electrically isolated from each other. And access to one cell as a result affects the values stored in other memory cells. This is due to electrical interference between the cells themselves and between the wires used for accessing those cells. This is also called cell-to-cell coupling or interference. So an intuitive explanation. There are multiple device-level explanations for it that I'm not going to go into. I'm going to draw the abstraction level over here. But when we activate or apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in that adjacent row lose a little bit of charge. And if you do this activation many times, or Rowhammer happens enough times, charge in such cells get drained. Of course, assuming that the cells don't get refreshed periodically in between. And today, we're at a point that cells cannot get refreshed that frequently. Essentially, today, I will show you some results. Today, where you can only do, let's say, 10,000 activations, and you can get these bit flips. The number of activations you can fit within a refresh period is 1.4 million. So basically, today we can do these activations very easily to induce bit flips. That's the technology scalation. And this simple circuit level failure mechanism has enormous implication on upper layers of the transformation hierarchy. Essentially, you get a bit flip over here in the device. It affects directly your programming language, algorithm, a runtime system, everything basically evolved. And I will show you that people took advantage of it. So let's go a little bit higher level. This is a simple program that we released together with our paper in 2014. It's on GitHub. You can still find it. You can try it on your laptop. I don't know if it still works. Google has a better version, so you can make Google. There are actually many, many better versions right now. If you want to attack your own laptop, you can feel free to do so today. But this simple program, what this does is, you can see that it's an x86 program. It selects addresses X and Y such that they map to the same bank in DRAM, but to different rows. And basically ensures that you bypass the caches in the processor so that you activate the rows. And you basically activate the rows in a ping-ponging manner. Essentially, this is what the program does. X, Y, X, Y, activate that. Basically, it does activates to different rows. And you can only have one row activated in a given bank. And if the chip is vulnerable, hopefully you'll get a bunch of bit flips over here. And that's what we showed essentially. At the time in 2012 or so, when we were doing the experiments, we showed that Intel and AMD systems are vulnerable. Don't worry about the numbers, exact numbers. These numbers have increased a lot right now. This is from 2012. We're talking about 10 years ago. Okay, so what's interesting about this? We said basically this is a problem. We said if you look at the first sentence of the paper, it says memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. And we said that if this is happening, then somebody can write a program that could hijack your computer. And we actually believe that. We were actually working on it. But there are other people who were much better at taking over the system, like Google Project Zero. These folks published a blog post in 2015 where they said that they actually did this. So I'm going to copy and paste from their blog post. They have a beautiful black hat presentation also. This is Mark Seaborn and Thomas Julian. They basically, these are copy and paste from the blog post. They basically said they learned about the problem from our paper. They tested a selection of laptops and replicated the problem. They built two working privilege escalation exploits that use the effect. One of them takes over the Google native client, not so interesting to me. The other is very, very interesting. It takes over as a user level program x86 for Linux. Basically, you become root on a Linux system. So how do you do that? If you want to go into the details, it's a beautiful attack. It's a new attack, actually. It introduces a technique called page table spraying. Basically, as an unprivileged user level process, attacks memory, if you will, and it tries to concentrate to induce bit flips and page table entries. So if you know virtual memory, page table enables access protection to physical memory. Now, if you actually somehow gain access to change your page table entries, you can change your access control to any part of your physical memory. And that's essentially what they did. They were able to gain write access with a user level process to the user level process own page table. I think of this as flipping the right enable bit, for example, access. You have a page table entry and access control bit says, can you write to this page table? And normally it's supposed to be 0, meaning that you cannot write. If you flip that bit, you can write to the page table essentially. Essentially, that's what they did. Of course, it's more sophisticated than that because attacking 1 bit out of 64 bits is not easy. They did a much more interesting attack that I'm not going to go into right now. But basically, they were able to gain read access to all of physical memory. And once a user level process is able to do anything to your physical memory, all bets are off. They can become root at that point. They can destroy your entire system. So, okay, that's the fascinating part. That's why people started drawing pictures like this. It's not my picture. It's found on the internet. Let's say, and a famous hacker, a very well-respected hacker on Twitter said, Rowhammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So if we're stuck in this room, don't worry. We start banging on the walls. And if the Rowhammer vulnerability is in effect, hopefully the door will magically open because of the disturbance effect. Okay, so later, a lot of security work ensued. I'm going to give you a retrospective at the end if you have time. But these are folks from TU Gaz that show that they can gain unrestricted access to the website visitors remotely inducing Rowhammer. These are folks from Vrije University in Amsterdam. And these are top conferences in security, as you can see. They can gain control of a smartphone deterministically by inducing these bit flips in the Android phone. You can still download their code, I think, if you have an Android phone and try if they can gain access. And you can actually do these attacks much more faster using a GPU. You can do it across the network through the RDMA remote direct memory access engines, and these folks actually did similar things. And even if you cannot take over a system for whatever reason, these folks show that the Rowhammer breaks confidentiality. So the previous attacks were breaking integrity of the system, right? Integrity meaning that you basically corrupt the data and take over the system. But even if you cannot do that, you can actually break confidentiality, meaning using Rowhammer, you can leak data from some other process to your process, and you can read some private data that you should not have access to, like a secret key. Okay, and then later people actually started neural networks using Rowhammer attacks, and this paper, for example, showed that a perfectly good neural network that would otherwise make reasonable decisions, let's say, when self-driving. I wouldn't say 90% accuracy is good today, but it's much better than, let's say, 10% over there, right? So if you actually induce bit flips at the right places carefully, you can actually destroy the accuracy of neural networks. Basically, that's why I have this picture of the self-driving car, because neural networks are everywhere over there. But if somebody attacks you with Rowhammer, that self-driving car is a disaster to be in it. You don't want to be in that car, or you don't want to even touch that car at all, or close to that car. Okay, I'm going to skip this one. So maybe this is another hammering mechanism, another attack or another solution. So these attacks keep coming. I will talk about the 2020, 2023 perspective soon. But while we were working on it, there were a lot of solutions, and we were invited to write this retrospective paper. This was written in 2019. So it's a bit old right now. I'm going to show you some more retrospective papers later on. This is the more recent one. Even this one's old right now because there have been work that has been done after this, which I will briefly talk about soon. Okay. So since we don't have time, I'm going to skip the understanding part, even though this is really important. If you're interested, you can read the paper for more detail. And we have papers that are later than this. This is the original paper where we introduced the Rowhammer problem. And we did a lot of studies to understand it, a lot of modules, as you can see, that study the scaling problem. And there are a lot of interesting things over here, which I will not go into because we don't have time, unfortunately. So if you're interested, you can read it. But let me mention this one. For example, one way of solving the problem is increasing the refresh rate. Refresh cells more frequently. But remember, what we were trying to do earlier when we built this infrastructure was to get rid of refreshes. So you can actually solve Rowhammer by increasing the refresh rate in a huge manner, 7x frequently. But that's terrible for energy and performance. So you can see there are two scaling problems in the IEDM. One is retention times, and the other is Rowhammer. You can solve one by worsening the other one. And this is actually very fundamental. This is very unfortunate. They go against each other. Okay. So this is the solution that industry built initially. The very bad solution, but that's an easy solution to do. So data pattern, there's also a lot of data pattern dependence. So it depends on the data pattern. Coupling effects are very much dependent on data pattern. Okay, I will not go through this. I will mention one thing over here. Error correcting codes don't correct the problem. Errors are repeatable, which makes a security problem. This is actually interesting. In our paper, we observed that if you choose rows X and Y and sandwich one row in between, you get a lot more difference. So this is called double-sided hammering, and Google did this actually in a very nice way later on. Okay, so Rowhammer is getting much worse. I'm going to talk about some of these papers soon, but not all of them. Let me talk about solutions before I go into like later papers. So what did industry say? Initially, industry, basically, if you have this sort of problem, you need to have two types of solutions. One is immediate, because there are lots of chips vulnerable in the field. All of our infrastructure is depending on DRAM. And the persons who are going to do the attack on you, they're not going to tell you that they're doing the attack. So people always ask in hardware security issues, are there known attacks? It's sometimes very, very hard to know these attacks because they're happening under the purvey of the software. Right? So I think it's a very, not the greatest question to ask, are there attacks happening? If there's a vulnerability, how do we fix it? Is the best question to ask. Right? Because you may not know that there's an attack happening, but it may be happening. Right? So immediately we need to protect the ships outside and also that are out in the field. And longer term solutions should be much more robust. Now, of course, you have limited possibilities with the immediate protection because you don't have a memory controller that you can configure easily. You need to change the hardware more. So what can you play with? So we propose both types of solutions in our original paper. I'm not going to go into the details of this, but these are some general solutions. Make better DRAM chips, unfortunately very costly. Refresh frequently. This is what's adopted by industry. Of course, it's not good. But this is the only thing that you could do easily by doing a software update to your memory controller. We're going to talk about that. Sophisticated ECC, I don't think ECC is a good solution to this. We will discuss that later on maybe. And access counters are interesting. We're going to talk about that later. So this is industry solution. Apple was nice enough to actually put it online. They basically said, Rowhammer is a no problem. And it was, they nicely cited our paper also, thanks to industry who actually cites papers. And they basically admitted that this issue was mitigated by increasing memory refresh rates. They didn't tell how much, probably 2x, maybe 4x if they're really worried, but even 2x is bad, let's say. You don't want to refresh your memory more frequently. And essentially all industry released similar patches, which I'm not going to go into. Okay, so what was our solution? Our solution was actually initially implemented by Intel memory controllers, but they were disabled later on because the DRAM industry said, oh, we solved the problem, don't worry about Rowhammer. So that's the story of Rowhammer that I will discuss soon. So our solution was very simple. It requires changes to the hardware memory controller. Basically, it's called probabilistic adjacent row activation. After closing a row, the memory controller flips a coin and with some low probability activates one or both of its neighbor rows. If you do that, you're refreshing the row essentially, but very low probability. And we showed that you get a great reliability guarantee with low probability. And if you're paranoid, you can increase the probability. But it's much, much better than increasing the refresh rate across the board. You're just refreshing the adjacent rows that are potentially affected. So that's the idea of it. And this is low cost, it's stateless, it's very, very low cost actually. This is the lowest cost solution that we have today. Unfortunately, it doesn't scale, as I will show. So this is not a good solution today. It was a good solution 10 years ago. Okay, And we discussed how to implement in the DRAM chip and the memory controller, etc. I'm not going to go into the details, but in the end, Intel implemented it. This was one of the earlier solutions. In fact, Intel gave you a choice. If you bought an expensive machine, you were able to have the choice of whether you want to have 2x refresh for Rowhammer solution or hardware Rowhammer protection. If you choose hardware Rowhammer protection, they don't disclose exactly what they do, but with some activation probability, they would activate some rows, similar to probabilistic activation. And you don't want that probability to be very high. You want the probability as we propose somewhere over here, which is what these people show. Okay, so that sounds good, right? Intel implemented a solution. So everything should work going forward and people should implement better solutions. Well, that's not quite how it works. So, but before I go into that, I should say that this is an example of an intelligent controller that we need to have, I think, so that we can have security, safety, reliability, and scaling. I believe there's no other option over here. And we actually have intelligent controllers in the flash memory, which was our inspiration. This is our infrastructure for flash memory and SSDs, which I will not talk about. And if you're interested, you can read papers about it. Okay, so let me jump into what's happening. What's happened since 2020? Okay, Intel implemented. So what DRAM manufacturers said to everyone, not just actually people who are buying this, but also the larger industry, they said they solved the problem. Don't worry about Rowhammer anymore. We're done. And unfortunately, a lot of people took it for granted. So we questioned it. Of course, you have to question everything, right? We said, is it really solved? Let's take a look. So basically, we did the study on an even larger number of DRAM chips, which was published 3 years ago in ESCA. We revisited Rowhammer. And basically, these are the key takeaways after 1,500 chips. So we basically said newer DRAM chips are much more vulnerable to Rowhammer. More bit flips happening earlier. So for some chips, after only 4,800 activations, you get a bit flip. How do you solve it? So we've actually questioned how can you actually solve this easily without disclosing what you did? So newer chips are more vulnerable, and existing mitigation mechanisms that are known to us are not effective at future technology. That's basically what we reported. We actually built a lot of infrastructure for this, more infrastructure than what I just showed you earlier to understand this. And again, I'm not going to bore you with the details, but this is actually a huge technology scaling study with many different chips that are used in different computing systems. And essentially, this is what, let me show you one example over here. So these are old chips, these are new chips. You can see that the bits error rate is shifting to the left and higher. Essentially, the bit error rates of new chips are higher. They also shifted to the left. What does shifting to the left mean? The hammer counts that are needed to induce that bit error rate is much, much lower, as you can see, compared to the older chips. So essentially, this problem is getting worse, and this was very strong evidence that motivated industry to actually take it much more seriously. Basically, people who read this paper, usually Microsoft and Google, said, look, we have a problem here. Our data centers are going to use these chips. Did you really solve this problem? Okay, so I can bore you with more details over here, but I'm going to skip because we don't have time. Essentially, we also showed that existing mitigation mechanisms that we know of are not actually able to deal with this nicely. So this is old technology. As you go from left to right, we're going to the new technologies. You can see that the newest technology over here, we're marching towards much smaller hammer counts to induce these bit flips. We're actually probably somewhere over here today, as we will discuss. Okay, so basically we said that we need to actually be more open about this, and we need to solve this problem seriously. Now, thankfully, there are some other industry that also said that. Now, this is interesting. This was a device level study. You can learn more about it. But at the same time we were doing this study, we did another study. Now, this was more collaboration with researchers who were working on Rowhammer security aspects a lot. And we basically asked the question, there are these DRAM chips that people are telling us are Rowhammer free. Are they really Rowhammer free? Let's try to attack. And that's what we did. We basically found out that you can actually come up with a real attack using real software and actually induce bit flips on these DRAMs that are claimed to be Rowhammer free. So this is the first work that shows that these protected chips, protected with some unknown mechanisms, that's called TRR, target draw refresh, but we don't know what it is actually. It's a very umbrella term. They're vulnerable to Rowhammer in the field. Mitigations advertised as secure are not secure. So basically, we introduced a many-sided Rowhammer attack because you could not do it with double-sided Rowhammer that I just discussed. The idea is to hammer many rows to bypass these mitigations by overflowing some proprietary internal tables that are in the DRAM chip that are there to detect aggressor. We don't know what it is, but we reverse engineered enough of it so that we can overflow them. And essentially, we also provide an automatic tool that can effectively create many-sided Rowhammer attacks. So this is the idea basically. This is a many-sided Rowhammer attack. You have 2 rows and then another row. This is a 4-sided Rowhammer attack. Again, you see bit flips after 9-sided Rowhammer attacks over here. So you need to have 9 rows. but you do see these bit flips because you actually bypass the mechanisms. Again, the reason why we were able to do this was because we had this infrastructure that enabled us control over the chips. Okay, I'm not going to go into the details, basically, how do you do this internally. It's very, very interesting, but we don't have time. I'm sorry. If you're interested in reverse engineering is extremely important for security today, and also understanding the security of your system. Reverse engineering is important because you will not have all the details given to you, as we can see over here, right, from the DRAM manufacturers. But we reverse engineered enough to induce bit flips. And this is our table. We were not able to induce bit flips in every chip. We were able to induce bit flips in 30% or 33% of the chips we tested, but that was enough for us because we were able to induce bit flips in all manufacturers, some of them more so than others. But some of them, for example, the best pattern was 19 cycles. Meantime, we have 19 different rows in a bank. Okay, this is very interesting, and then we showed that actually you could do this attack on real cell phones. And we used some known Rowhammer attacks, like page table entry attack. This is from Google. And then there were other attacks that were developed to take encryption keys and essentially destroy your security on the web, let's say. There are a bunch of attacks, and you could do these attacks on these chips that were advertised as Rowhammer. Okay, sounds interesting, right? This is the takeaway, essentially. So we said at the time we wrote the paper, we said that these are not exhaustive. We're building a proof of concept, but this shows that Rowhammer is still an open problem, and security by obscurity is likely not a good solution. So we basically encourage the manufacturers, don't do this. Don't be obscure. And I think this is actually very true. If you're obscuring something that you probably don't trust your algorithm, it's much better to be open about how you solve the problem and let people attack. And if they cannot find any solution, any hole over there, that's great. That's really the solution to security, especially in an area like this, where all of the systems that we have are affected. Okay, so if you're interested, you can learn more. Okay, so we also worked with Microsoft to really understand how do you guarantee Rowhammer chips are Rowhammer free, and we don't have an answer to this basically. It's very difficult to guarantee a chip is Rowhammer free today, but if you're interested, you can read papers. Okay, so we said that we were reverse engineering, and we were able to induce these bit flips only in 1/3 of the chips we tested. We said, then we asked the question, can we do even better? Now we developed a methodology in this work that essentially is able to uncover the inner workings of what DRAM manufacturers did internally completely. So you can actually completely expose what is done. As a result, you can build attacks that are much better. And we basically show that all modules that we are looking at are actually vulnerable. And you can actually get bit flips in 99.9% of the rows in memory. And you can get a lot of bit flips in a particular row, making error-correcting code, even very strong ones, ineffective. So this paper developed a methodical approach to actually do this automatically, if you will. And we basically conclude essentially the same thing, but it's much worse, basically. It's not just 1/3 of the chips, it's actually all of the chips that you can test is vulnerable. Okay, again, I will not bore you, but this is very interesting because this is where data retention failures and Rowhammer again becomes interesting. We use data retention failures as a side channel to detect when a DRAM chip is internally refreshing a row. So if you know enough about the retention properties of the cells, you know that a row is not going to be refreshed periodically. But if an internal refresh happens, that must be happening because of an internal protection mechanism that's there. So you can actually reverse engineer this way, and that's what we did. And of course, you need to do it with an infrastructure like this. Okay, I will not go into detail, but you can see that different manufacturers actually employ different types of mechanisms to solve this problem. They have different types of configurations. Some of them we couldn't discover completely, but that was enough to actually induce errors. And you can actually see the numbers over here. There are lots of errors that you get. Okay, and ECC is not effective. Okay, I'm skipping a lot of these slides because we don't have a lot of time in this particular lecture, so that we can go into later. So later, actually, interesting things started happening. Finally, Google published a paper in 2022 that basically said, oh, we have another type of Rowhammer attack. Basically, these other Rowhammer attacks were inducing bit flips with a heavy aggressor row, and then immediately adjacent row was getting bit flips. But Google said that you can have a very heavy aggressor row activating a lot, and then you can have another row that you don't activate a lot, likely, but then there's a victim row. So you can actually have this effect across different rows, as you can see. This actually has implication in terms of solutions. So if your solution is refreshing the adjacent row, this actually solution itself is becoming an attack in this case. So it's very interesting, and they actually talked about this. And if you're interested, you can read Google's paper. It's called Optimal. It appeared last year, even though they developed the attack row. Okay, so how much time do we have? Okay, we have some time. So I'm not going to go into a lot of these characteristics. So we've been doing a lot of studies to understand the characteristics. These are extremely important in our opinion, because if you don't understand some of these characteristics, an attacker who understands these characteristics can use them again. So if they understand, for example, how temperature affects Rowhammer, they can actually change the temperature of your system. If they understand which victim cells are actually more important to attack, they can focus their attack. So these are actually important properties to understand from both attacker perspective and a defender perspective. And openly providing this data out there is very important in our opinion. So we built even more infrastructure for this because you need to actually look at temperature-defined granularity over here. Okay, now after this point, we started writing the names of the manufacturers basically. We don't say ABC. It's fine now. You can be exposed anymore because you did the wrong thing once, let's say. Don't do the wrong thing again. Okay. Again, I'm not going to go into the details of this, but it's very interesting. For example, there's a paper coming up at ISCA that studies this effect to the next level that I'm not going to talk about in detail. But if you keep the aggressor row active for a longer time, the attack becomes worse because you induce some other mechanical issues or let's say electrical issues that actually cause problems in the cell. This is very fascinating to us. It's actually much worse than what's depicted over here. Let's read this paper if you're interested in that. I'm not going to talk about that right now. So let me skip some of these. Let me talk about solutions. There's a lot of interesting things over here. It's in the deeper look paper, and you can watch Guy giving the talk if you're interested. There's more Rowhammer analysis, like how does voltage affect things, which is also interesting. Voltage is not a solution, unfortunately, because it has a lot of effects, which is not easy to just focus on Rowhammer. Okay, let me talk about solutions. So we developed this block hammer solution, which I think is interesting and was actually named as a finalist in Intel hardware security contest in 2021. Let me give you the broader picture. Essentially, we already discussed that these are not good solutions. People try to physically isolate rows. That's not a good solution. People have shown that. These two solutions are the solutions that are remaining, let's say today, which is reactive refresh, detect an aggressor row and refresh adjacent rows somehow. Detection could be probabilistic or deterministic. Or detect aggressor rows and proactively throttle them, meaning don't access them for a while before you induce a victim. So these are actually two interesting solutions. Blockhammer does it this way. And unfortunately, there's no perfect solution. It's all post-prover performance complexity. It's a huge trade-off space over here. The key thing is guaranteeing security is important, basically. Assuming you guarantee security, it should not be part of this trade-off space. You should not have bitflips, basically. That's what guaranteeing security is. So we wanted to solve the scalability challenge and compatibility challenge over here with Blockhammer. Scalability is, Rowhammer vulnerability is becoming worse. Your solution needs to be scalable to smaller hammer counts. And also, you should be as compatible as possible with commodity DRAM chips. And that's what we did in this work. Again, the idea is to selectively throttle memory access that may cause Rowhammer bitflips. Let me give you the very high level. I will not go into detail. You can read the paper, etc. But basically, a Rowhammer attack hammers row A. Blockhammer detects a Rowhammer attack using area-efficient Bloom filters implemented in the memory controller. And it selectively throttles accesses from within the memory controller such that that row is not being attacked anymore, such that bitflips do not occur. So, of course, you need to have a security proof to make sure this works. And we have a security proof. And you can optionally inform the system software about the attack. So you can basically say, look, I stopped someone hammering your row. Maybe you should do something about it. I think this is a good solution, actually, because you cannot solve the problem completely in hardware. You don't know what's an attack and what's not an attack, basically. There's no need for proprietary information from the DRAM or modification of the DRAM chips, which was a sticking point with a lot of the manufacturers. Okay, let me skip these since we don't have a lot of time. If you're interested, feel free to ask questions. But basically, the performance overhead of this is not bad. It's as good as previous mechanisms that are much higher cost. And when their Rowhammer attack is present, Blockhammer is actually much better because it throttles the attack. The attacker becomes less and less intensive over time, essentially. So that's the good part. The attacker is contained much better with Blockhammer. And this is also important for energy consumption because if somebody is attacking your rows and if you throttle them, you're reducing the energy consumption of the system. Okay, I'm going to skip these also. But the paper, we actually open source this. You can actually download it if you want to develop solutions. That's great. You'd be happy to support. But this is an example of an intelligent controller that's actually stopping the attack, if you will. And so it's helping security, safety, reliability, and scale. But unfortunately, solutions are not perfect. I don't believe Blockhammer is a scalable solution. If you can induce bitflips with, for example, only 100 hammers, now some real programs start hammering DRAM. It's not an attack anymore. Some real programs actually activate a row 100 times within a refresh interval. So how do you now solve this problem? This is a very bad technology scale problem where real programming can start becoming bit flip inducers. So let's talk about that maybe a little bit. There are other solutions which I'm going to skip. I don't think these work very well, but they're published. You can take a look at them. Yeah. So let me cover what has happened in 2020, 2023. I didn't do justice to all of the literature, but you can see that major conferences, micro, there are actually Rowhammer sessions at major security conferences today. Some other security conferences, even operating system conferences have these papers. Yeah, more security conferences, more architecture conferences. This is actually last year. There were multiple papers over here, and you can see very interesting papers also. For example, these folks, that's the Deep Steel, they basically said, we think with Rowhammer, a proprietary deep neural networks weights, you can actually get all of them. So if Google is hiding their proprietary neural networks weights in their edge neural network system, using Rowhammer, you can actually reverse engineer all of those weights. So you can actually get a lot of private information over here. And then other conferences you can see. I don't have time to talk about this, but certainly reliability physics, all of those conferences are also talking about Rowhammer. Let me come to 2023 or so. We also have some other solutions that I'm not going to discuss. And we also write some papers that encourage essentially the whole industry to be more transparent about these reliability issues. I like the solution, so I'm going to give you the idea very, very quickly. The basic idea. A lot of the problems in DRAM happen because our interface doesn't allow the manufacturer to do things independently. Meaning, so I was very hard on the manufacturers for not solving the problem. But one of the reasons why manufacturers are not able to do things easily, other than their mindset, is DRAM chip doesn't have a lot of independence. It has no independence actually. The memory controller is very strict on the DRAM chip. DRAM chip cannot do anything by itself. So that's what we argued in this work, basically. DRAM chip should have some independence. Basically, the key idea is to prevent the memory controller from within the DRAM chip from accessing the DRAM regions that are under maintenance. Under maintenance can be refresh. Under maintenance can be some error detection. Under maintenance can be Rowhammer maintenance. And that's the idea. Basically, we propose the mechanisms, very low cost, that can actually help all of these problems. So I think this is the way to go. It requires a simple change to the interface, which is not that bad in our opinion, but a lot of things that are very hard to change in the memory industry. We can talk about that why. But this is part of the thesis of my last graduated PhD student, Hassan, and I believe this is the way forward going into the future. But of course, there are a lot of interesting things to examine here also. So this was in 2023. You can see another Rowhammer session in IEEE security and privacy, which is interesting. There are both solutions and attacks. So both of them are happening. And HPCA also has some solutions. Now let me mention what the industry did finally. This is last month, February 2023. This is a paper from SK Hynix, which is the second major DRAM manufacturer. They finally published a paper saying that Rowhammer is a problem. In 2023, that's 9 years after we published our original paper, which is good, I think, which is progress, right? And they basically said that they provide some new mechanisms, not new mechanisms, they don't say it. They provide some mechanisms to solve the problem. And a lot of them are inspired by our prior solutions. You can read them. It's interesting, but even they did not solve the problem completely. They don't talk much about exactly how they did things, but it's good that they're talking about it. And the solution is basically adding some counting, like access counters to the DRAM node. So they actually bit the bullets, and they add a lot of hardware to their DRAM to solve the problem. So this is what we envisioned in 2011 or so, let's say. And it's good that this industry is doing it, but maybe my message over here is be patient in research. Eventually, if you have a good idea, a good solution, it may happen after 10 years, it may happen after 30 years. It may not happen while you're alive, but maybe someone else will pick it up and make it happen in the end. So it's not only SK Hynix, so Samsung was also open about it. They didn't write a good paper like SK Hynix. They wrote another paper like this that's very hard to read. But solutions are inspired by prior probabilistic mechanisms. You can see that stochastic and approximate counting over here. Now, Rowhammer is still going on. This is DSN, which we're organizing at the end of June, and there are 4 Rowhammer papers, one of which is ours. We look at high bandwidth memory chips. And if you're interested, ISCA, we're going to reveal a similar or somewhat similar disturbance mechanism, not similar, it's actually orthogonal in the end, that makes this much worse. Basically, in this paper, we show that in an extreme case, you can actually induce bit flips with one activation. Only a single activation causes bit flips if you wait long enough for the row to be activated. And we show that you can actually do this, not one activation, but you can actually reduce the activation count needed to induce bit flips by 2 to 3 orders of magnitude compared to Rowhammer. in real systems, and also real chips as well as real systems like an Intel system. Okay, I believe there's more to come basically. So since we don't have a lot of time, I will say that basically this is becoming worse. DRAM is becoming worse, and other areas may be appearing that we don't know what. Redisturb is one example clear. Retention errors. I strongly believe that retention errors are slipping into the field because testing for retention errors is very difficult. Even though manufacturers added ECC into their systems. So these errors can also pose security vulnerabilities. I don't know of any research that has shown that one can take advantage of the retention errors to take over a system, but I believe that that is bound to happen if we don't do something about it. And other memory technology, you can say, okay, DRAM is old technology, I don't want it. True, I don't want it in some cases also, but we cannot replace it, unfortunately. Unfortunately, all of those emerging memory technologies have some problems, and they're not there yet to replace DRAM. So we're going to be bound to DRAM for some time. And flash memory, for example, we heavily examine flash memory, and there are lots of areas over there also. How do they solve the problem? There are a lot of intelligent controls in flash memory. And again, I don't have time to talk about it, but intelligent controls can be quite intelligent. Okay, so that's my takeaway basically. We need intelligent controls to solve these issues. And we can avoid many failures and enable better scaling, better security. So I'll skip this. We need to do a lot of understanding, architecting, and design and test. So there are two major future directions in Rowhammer: understanding Rowhammer and solving Rowhammer. There are a lot of other issues that we still need to understand. And solving means to be much more efficient and flexible and co-architect system and memory. But then there's also what other error mechanisms are lurking out there. That's another question. It's not just about Rowhammer in the end. So this is what we argue in this recent paper. Let me jump into bridges. So these are bridges. Like we have been building bridges for thousands of years. We have not gotten it right. This is Seoul in 1994 on Han River. This is Minneapolis in 2007. This is Genoa. And more recently, this is Pittsburgh, where I used to live. I used to go over this bridge, and this bridge got destroyed on Forbes Avenue. And it's a beautiful picture, but you don't want to be on that bridge. You don't want to be on that bus or car over there. At the time, there were no fatalities in this one, but there were fatalities on the other ones that I showed, except for the first one. So basically, we have not figured out how to build bridges. I believe we can figure out how to build computers better, in the sense that computers are a bit softer, right? We can patch things. With bridges, they're heavy infrastructure. How are you going to patch something? You can build, of course, 10 bridges on top of each other. They can all collapse on top of each other. Basically, the problem is a bit more urgent in computing, and also a bit maybe easier, because maybe I understand this better. So we need to really have in-field patchability to avoid these failures. That's what we've been arguing for. And the good thing is industry has been arguing for it also, even though they didn't talk about Rowhammer. It's a paper from industry in 2014, where they said, we're having a lot of difficulty with DRAM process scaling. This is the only paper that I know of that was written by these two companies, Samsung and Intel together. Normally, these two companies don't talk to each other, unless they have an army of lawyers on both sides, right? Two armies of lawyers. So they basically said, we should solve the problem by having more intelligent controllers. Now, they're doing it finally, but it took a while. That's what these papers are about. Okay, so let me give you some final thoughts. So how many people know about Byzantine failures? Distributed systems. Nobody studied distributed systems. We all knows about it, I know. But this is an example of a Byzantine failure, actually. And this is a very nice story about the Byzantine Genome problem developed by Leslie Lamport, who is a Turing Award winner. I borrowed the slide from my colleague at CMU, Satya, who teaches the distributed systems class, and he was very famous in distributed systems. After he learned about Rowhammer, he said that I'm going to put it in my class immediately, because it's an example of a Byzantine failure, and people should solve. Basically, Byzantine failures are characterized by undetected erroneous computation. When you have erroneous computation, you should either fail fast with an error or no result. Stop basically doing computation. But here we're continuing computation, right? Erroneous, because as you compute computation, you can have an error, or someone malicious can take over your system. Intent is the only distinction. So it's very difficult to detect and combine this sort of Byzantine failures. Do all you can to avoid them. And if you're interested, this is the Byzantine Genome paper that basically talks about how generals that are communicating to attack a city, Byzantine generals, essentially the Byzantine Empire, which is close to here, as you know. Well, I guess these parts used to be part of the Byzantine Empire at some point, or the East Roman Empire. Essentially, these generals are communicating with each other. Some of them may be traitors, meaning some of them may have bit flips. Because traitor can be a traitor because intentionally they're a traitor, or there's a failure mechanism. They could not deliver the message because there was a failure mechanism, right? So how do they actually coordinate as a distributed agent so that they can attack the city? And this result shows that you essentially it's here. You can see that it's shown that using only oral messages, this problem is solvable if and only if more than 2/3 of the generals are loyal. So you should have at least 66%, 66.6% of your generals that are loyal. Okay, very interesting, but I'm not going to go into it. Let me give you another story. So before Rowhammer, people knew about bit flips. So we didn't introduce bit flips clear. Bit flips were happening. And these very smart folks from Princeton University in 2003, as you can see, published a paper saying that we can use memory errors to attack a virtual machine, meaning a Java virtual machine is running. I induce memory errors, and I'm going to take over that virtual machine. You should not be able to take over a virtual machine. The way they did it was using this lamp. They have this lamp, they shine light on the memory, they get a lot of errors. That's great, and then they take over the machine. So yeah, this is not a viable attack. This is a beautiful paper that I read. I enjoyed it a lot. I said, maybe we should replace this lamp with Rowhammer. So essentially what Rowhammer did was this, it replaced the lamp with software. So you can induce these bit flips in a very targeted manner using software. You don't need that physical access, you don't need that lamp at all. And as a result, security community took actually advantage of that. Here, security community thought this is a very interesting attack, it's a very niche attack, nobody's going to do it. How do you actually get physical access to someone else's machine to do this? If you have physical access, maybe you can do even more things than using a lamp. But if you don't have physical access, if your software can induce bit flips remotely or anytime you run it, that's what Rowhammer is. Okay, so I think the mindset that's enabled by Rowhammer is very interesting, I think. That changed the mindset in the security community. Security community now started thinking that real memory chips are vulnerable in a simple and widespread manner. This causes real security problems, so we should go into it. And essentially, hardware reliability and security connection is now a mainstream discourse. So many new Rowhammer attacks are being developed. I've shown you some examples. I believe there's more to come. But of course, the bar is higher right now because solutions are being developed also. Many new Rowhammer solutions are developed. I've shown you a bunch of these also. And I think there's more to come over here as well. But I think perhaps most importantly, the mindset shift is very interesting because you see a relatively small amount of hardware security research in the security community before Rowhammer. Once Rowhammer papers started appearing, the snowball. Basically, people started thinking general purpose hardware is fallible, its problems are exploitable, we should exploit them. Because, and also people are always thinking the root of security is in hardware, the root of trust is in hardware, but this really experimentally demonstrated. So that's why you see a lot of hardware security papers. So as a result, some system security researchers examine hardware in more depth. They try to understand hardware even more. And I believe it's no coincidence that two of the groups that discovered Meltdown and Spectre, these are side channel attacks on a wide variety of processor chips. They worked on Rowhammer attacks before, and they still keep working on side channel as well as Rowhammer attacks. So I believe there's more to come in hardware security. There's a lot of interesting things to do over there. Now let me conclude. I think hopefully I've convinced you that memory reliability is reducing. Reliability issues open up new security vulnerabilities as well. These are very hard to defend against. Rowhammer is a prime example of this. It's really the first example that we know of how a simple hardware failure mechanism can create a widespread system security vulnerability. And its implications of system security research have been tremendous and exciting. It's inspired a lot of people. It still continues to inspire us after, let's say, I guess, 12 years since we first started studying the problem, basically. The bad news is it's getting worse. And there are other mechanisms that could be causing bit flips, as I just discussed. Good news is we have a lot more to do as researchers and security people, let's say. We're now fully aware hardware is easily fallible. We should never say that hardware will not have bit flips, for example. We're developing both attacks and solutions, and we're developing principled models, methodologies, and solutions, hopefully with a better mindset, in the sense that we should really be open about solutions, put them out, and get it attacked. That's the way to actually make progress. Okay, I'm not going to go through this. There's a lot over here, but I will thank people who helped us in this research. Certainly people who supported us, like Intel, and more recently, Google and Microsoft that are supporting this research significantly because they're the ones who's going to be affected most, perhaps, in the end. If these bit flips happen in their data center, they're vulnerable to everything, right? So more so than the manufacturers, I would say. So they're pushing the manufacturers to actually do the right thing. That's and of course, my research group who've done, well, not everybody, but who, a significant fraction of the research group have been working on these issues. And you can see some faces over here. And I believe we've just released our new newsletter online as well, so you can take a look at that. Okay, I'm going to stop here. Thank you for your attention. I'm happy to take any questions. Yes, please.
Why, at the end, I didn't find explanation why error correcting codes cannot be used to install.
Yeah, sorry. I kind of I went through a lot, so the part that I was going to discuss it in more detail got kind of 10. So basically, so there are two reasons. One is principle, the other is reality, and both of them work against error correcting codes. Let me pick the reality. Reality is error correction. When you want to correct a bunch of errors, when you want to correct some errors in a block, if you look at how many errors Rowhammer used in that block, today that number is 7, 8, 9. So what we can practically do in modern error correction codes in DRAM chips is single error correction, double error detection. Okay, if you push it, maybe double error correction, triple error detection. If you push it, maybe 3 error correction, you see where I'm going right. So it becomes much more expensive as you increase the number of errors that happen. So that's the practical thing, or reality. I think reality is we know that you need to have extremely strong error correcting codes to protect them. And those are, yes, you can do it. In the end, you can actually have huge redundancy in your chips. It's going to be extremely expensive, also power inefficient, also performance, etc. Basically, it's against everything that we want. And the principal one is actually, I believe in this strongly. Error correcting codes are great at correcting or tolerating bit flips whose reasons we don't know, meaning usually random errors or something close to random. So random bit flips you can correct with low overhead with error correcting codes. Here we know the reason, we know exactly why this is happening. Maybe we don't know exactly everything about it, but we know that if you actually start hammering a row, you can actually correct it. Meaning there's a better solution. There's a much more efficient mechanism that you can use than protecting the entire memory with error correcting codes. So I think that's the principal reason. Hopefully that makes sense. I would rather use the error correcting codes budget for reasons that I don't know. Like variable retention time is a great reason to add error correcting codes because it's essentially a quantum-like effect. It's completely random as far as we know. We cannot predict it. Here we know exactly how to detect it. Yes, please.
Well, I would like to ask you to elaborate a bit on what are the scenarios where the solution could pose a threat.
The solution itself could cause a threat. Okay, that's a great question. So this is actually something that needs to be examined more and more going into the future also. Because with technology scaling, the solutions start engaging much more often, right? Because you're activating rows much more, you're causing bit flips, or you're potentially causing bit flips with fewer activations. So what are the scenarios under which solution can cause a bit flip? So the solution, for example, if the solution is refreshing adjacent rows, every refresh is an activation, meaning it's actually causing damage from a read disturbance perspective. So if you're refreshing some adjacent row very frequently, that solution could actually be an attack itself, right? That's what the Google paper showed. So you need to design your solutions such that they don't become attacks themselves. That's one scenario. The other scenario is solutions. Okay, refresh is tough because of what I said. Some other solutions throttle. What should I say? Throttle the attacks. Basically, they stop a thread that is accessing some row, right? Now, this causes some other issues, some quality of service issues. Meaning, if your solution is not perfect, if it's approximately detecting which rows are being attacked, you may be slowing down a thread. That's, let's say, innocent. It's not an attack. And this causes a quality of service problem, an unfairness problem, essentially. So you can convert Rowhammer to an unfairness problem, which is itself is a potential denial of service attack to the thread that's innocent. Yeah, I see these two things that are major. There may be other things, of course, that we have not discussed so far. Any other questions? Otherwise, Velko has another question, I think.
What about other memories? We see that in this kind of DRAMs, what's going on in this? Other available.
Other available. So, okay, let me go back to that memory slide. So DRAM is very special because unfortunately we don't have any good memory to replace it today. All main memory is DRAM for a good reason today. Where is this? Okay, there you go. Flash memory, if you have SSDs, similar things exist in flash memory. In fact, before we published our Rowhammer paper, we were working heavily on read disturbance in flash memory. This is getting much worse in flash memory also. And we were actually inspired by our flash memory studies. It's a slightly different error mechanism as flash memory. I don't want to bore you with the details, but this sort of errors happen in flash memory. Any scaled memory technology, as you reduce the size of the cell, there's this sort of interference that happens. And we see in flash memory that this is becoming much worse. It's become much worse. We propose solutions to it. Flash memory is nice because it's far away from the processor. You actually have a controller that's protecting the flash memory. So there's a lot of mechanisms that you can use in flash memory. So I don't believe that it's a big issue in flash memory, although there's an IBM paper that shows that it is somewhat of an issue. So IBM actually wrote a paper saying that you could do Rowhammer on flash memory. I don't quite believe it, let's say. The other memory technologies are interesting, and there have been papers that say that, for example, STT-MRAM, which is a potential candidate, maybe down in 10 years, replacing DRAM, but it could more replace SRAM memory on chip. It's actually interesting from that perspective. People have been writing papers saying that Rowhammer exists over there in somewhat different ways, and here are some solutions potentially. Because we don't have chips, we're not able to test them, unfortunately. These are done using simulation studies, for example. So essentially, other issues, I have not seen Rowhammer issues in phase change memory, but there are issues in RAM that we're working on right now, or ferroelectric RAM. So I believe all of these memories are actually vulnerable. As long as they scale to smaller nodes, I should call it read disturbance, not necessarily Rowhammer, because Rowhammer is very specific to DRAM. It's the fact that the commodity DRAM chips are vulnerable, in my opinion. It's an example of read disturbance. Read disturbance issues exist in all of these memories, strong or not, but some of these technologies are not scaled enough to see these effects. So even DRAM, for example, it was invented in 1968. The first patent was 1968. And the first error I showed you is from 2010. So it needs to scale to something, a small technology size so that you can see these effects. But I don't believe that there's any technology that's immune to this sort of isolation effects. You could make them immune by using much more expensive materials. There's actually some papers that talk about these materials, but in the end, cost is very high. You might want to have actually very high error correcting codes instead of those materials, at least currently. But that's a great question, I think. Like, how do you solve this at a technology level? Unfortunately, I don't see a great way of doing this. And also, there's another evidence over here, because I believe VM manufacturers actually tried very hard at their level of expertise, which is technology and device and materials, to solve this, and they're not able to solve it yet with VM. So they're trying. Yes.
There is a problem that is happening with DRAM. Is it similar as a problem in the transistor size and quantum tunnel resistance?
Yeah, so that's a great question. Basically, what are the device level reasons for it? Basically, that's your broader question, I think, right? So you can read our original paper that talks about some of the reasons, but actually, I'd rather say I don't want to go into the details of it because there are multiple reasons. So it's not just quantum tunneling, basically. It's actually there's, for example, there's some charge leakage, charge injection that happens from one place to another place. So charge leaks and it gets injected into the substrates around you. You could consider maybe similar to quantum tunneling, but it's a different effect in the end. I don't know if you know about the term hot carrier injection. That happens also here. So maybe I should report you to this retrospective paper that covers a lot of that. Even though it's not state of the art, it actually covers a lot of the, where did it go? I have so many slides. Okay, this retrospective paper from 2019. Yeah, this one. This one has a section that covers what are the device level reasons. And again, I should also warn you that there's not a complete consensus in this. The reason there is no complete consensus in academia is because industry is not talking about what they do exactly in their DRAM chips. And this is much worse, much harder to reverse engineer, obviously, right? Because now we're talking about device level issues. Okay, but it's a combination of multiple effects. Let me put it that way. Yes.
So we usually have a model for everything. And then for the given model, we try to develop effective solution. However, errors also appear from sources and for reasons outside the model. Our solutions, as a collateral can do eliminate some of those that happen from outside of the model. So the question is, in philosophy, what is to be done to increase the percentage of collateral benefit for a given algorithm that fights against error?
Yeah. Yeah, that's a general question in dependable computing, I would say, yes. So basically, the solution that helps other errors. So for example, I think refreshing helps other errors, solving some other errors, because some cell may be about to leak, and if you actually refresh it, because you think Rowhammer is happening in that cell, you actually restore the charge because of, and you solve the retention type of errors, right? So I think refreshing helps, but you need to be careful that it's also not an attack, as we discussed. I think error correcting code is another example. You may add error correcting code for some reason, and manufacturers did that actually for variable retention time. The reason they say is because they wanted to solve the variable retention time issue. But these error correcting codes can actually help Rowhammer as well. If you get a single bit flip, because you have an error correcting code, you're a bit less vulnerable. Maybe you don't fix all of the errors, but your vulnerability reduces. So I think a lot of these solution mechanisms help. I think redundancy is certainly that helps. I guess refresh is also redundancy, right? Redundant refreshes that you send, that also helps.
No more questions.
Okay.
Thank you, Professor.
Thank you.
Thank you all.
Okay. Yes. Oh, okay. Maybe I'll answer that with a question. How did you notice that detail on that slide? That's excellent. That's why he's a senior professor. He can notice this important detail, right? So yes, I guess he also appears in a lot of papers, right? So I think this is a matter of, let's say, national ID. While someone was putting his national ID, they didn't put. They somehow misspelled it. That's the story I have from him, at least. Yeah. So that happens more often than you think in places like, yeah, Turkey. Yeah. Yeah, certainly. I'm happy to.
Because it's very big.
Sure, yeah.